Yeah, so it just simplifies the
procedures.
Yeah. Okay.
All right. Can you hear me? Hello, can you hear me?
Yes, Ikaro.
Very good, thank you. My name is Icaro. I'm an ex-Run2 delegate. Here's a bit of a funny joke, like I was knowing Run2 at the beginning of NR days as the beam guy. Then this might be a bit insulting for some layer one colleagues who are much more experts than myself in beam forming, beam procedures and stuff. But at least in Run2, at the very beginning, since there were quite a few delegates working with NR, this was sort of the hot thing happening, and there were few people working with that also. And in Run2, there was also some level of abstraction, which made it easier to understand some impacts of beamforming technology. And the whole point was also because in NR, we aimed to have a physical layer design that addressed higher frequencies, and that would require beamforming to compensate for the coverage and the challenges in high frequencies, but also the opportunity of going to high frequencies and designing smaller antennas and so on. I think for the layer one audience, this sounds a bit more familiar, but that was the thing. So it brings lots of memories to me. I have a presentation on mobility because it was my first days in NR in Run2 also. And then I would take the opportunity to talk a bit about the history of mobility NR and what happened in Run2, since this is a Run2 seminar, and perhaps at some extent lessons learned. I mean, what happened and why it happened, and what could happen that didn't happen, and all those things. There was a lot of talk. There was a lot of talks about beamforming and having a beam-based system. And at that time, there was a thinking of perhaps changing a bit the cell concept in NR, and even challenging what would be done in RRC, which is one of the main protocols we standardize in Run2. And there was some thinking that perhaps we would not have a cell in NR because of beamforming. We would not use RRC for mobility. And here comes Run2 and says, let there be a cell in NR. And there was a cell in NR. And this is written in the Book of Chairman in the Run2 94 meeting, Chapter 9.5.1, verse on general requirements. And you can find that this was sort of one of the first decisions. And despite the thinking that we could get rid of the cell, and I just searched again, and this thing changes, but there are about 2,600 occurrences of the word cell in RRC. So basically, the lesson learned is very hard to get rid of the cell. And it may impact things that we think that don't exist, but it impacts more things than what we think. And we will go through some of these here, at least to some level. And this is the first agreement that I was referring to that Run2 had. And the agreement was that there are two levels of network control mobility. One is driven on RC level, and it said that it's cell level mobility. And the other one is zero minimum RC involvement, which is Mach and Phi. And this is basically this beam mobility if you are within the same cell. And while the first one is like when you're changing cell, you're still doing beam mobility, but you are changing other things, other parameters, and so on. And the two important keywords here is actually the things we were thinking that could be challenged, which is exactly RC and cell. And those are, let's say, two quite important keywords in Run2. So RC is one of the main protocols that we standardize. It's the main control plane protocol, at least. And many things are related to this concept of a cell. So the main goal of this seminar about mobility is, as I said, to tell a little bit of the NR mobility history. I will talk about NR cell concept, at least some aspects of it, and a bit of an overview of RC and connected mobility. At least I think it doesn't sound obvious when someone asks for me a presentation about mobility. I get the feeling that people have the impression this is handover, but there are many more things than handover, especially when you search keyword handover in RRC. You won't find everything you need to find, and perhaps even this word you may not find, as the procedure is not called handover in RRC. But that's more positive thing. but it's relevant when people start to work in the area and want to learn about the area. I mean, it's a bit frustrating. Like, yeah, look at RC handover. Oh, but there's no handover. Yes, I will explain a bit on that. The second, I will talk a little bit on deltas compared to LTE. This is the approach I also took in previous presentation I had on states. And by delta, I mean the differences, more from an RC point of view, but in some cases, I go a bit into physical layer changes that may require changes in RC. And those are the two parts when people talk about mobility. Sometimes it's not very clear how to make the split, but in RC, it's very clear that you have the RC measurements, which is a whole framework that is not only about mobility. Patrick presented, for example, this dual connectivity. Then when you go to the RC chapter on measurements, you will see that this is not just about mobility, but the setup of dual connectivity, the release of dual connectivity, the setup of carrier aggregation, and so on, also relies on this measurement framework. So it's not just about mobility, but some of the functionalities there are about mobility and perhaps how it started in the first releases in 3D and then LTE and so on. And the second part is the mobility itself, like what is the procedure when you have to change from one cell to another. And that relies a bit on the presentation that Henning had previous week about RC reconfiguration, which was the main message. And the handover in a way and the mobility in a way is a particular case of that when you include a certain field, which is this reconfiguration with sync, which is the official name of mobility intercell in NR. Why is this important? A service continuity, right? When the UE moves, we want to continue the service. We don't want to get packet losses, and we want the user experience to continue the same. We also want, from a system point of view, to let the UE always be connected to the best cell. Best can be debated, but at least from radio condition point of view, not to generate interference by being connected to a cell which is not the best in a given frequency. It's also a basic feature in RC, and it's both useful and to a certain extent implemented for non-standalone and standalone. So parts of it, for example, the measurements, I think this was standardized since NSA. When it comes to the cell concept, or at least some aspects that are relevant for this presentation, there was this question if a cell would be a set of beams. And in the first bullet, I just recap here, since we have many layer 1 colleagues in the audience, that in LTE and NR, we have these synchronization signals, PSS and SSS. And they, in the same way, in LTE and NR, they also encode a physical cell identifier. There are some differences, such as the number of identifiers we can encode. If I'm not mistaken, NR we have double or almost double number of what we had in LTE. And in both LTE and NR, they also work as a sync source. That's where the UE obtains the initial synchronization. These are the signals where the UE, let's say, initially searches for when the UE is looking for a cell. When you turn on the battery, the UE has some pre-configured frequencies it looks for and some sort of sync raster. And that's how the UE identifies a cell. Like the UE initially searches for it, does some match filtering, and then, okay, this is this PCI. I do cell search, and then I do cell selection, and I select the cell. So there is this notion of a cell since you turn on the phone. And from a physical layer point of view, it's how you detect this PCI thing. And then in LTE, I mean, I show on the upper right figure here this PSS, SSS, X encoding the PCI, and a little bit in a, let's say, omnidirectional way, or it could be directional antenna also sectorized. And then on the right-hand side on the bottom, I show a bit the NR aspect, which is that to define a cell, we have this PSS, SSS as in LTE, but then you can transmit them in different, which in an abstracted way could be seen as different downlink directions. And for the same cell, the different beams would transmit the same PCI, which means same PSS, SSS, but you could have a different beam index. We don't call beam index really. I mean, there are different terminologies, such as this SSB, which is this SS block. But there is a way for the UE to distinguish that I am in the same cell and I'm listing multiple beams of the same cell, thanks to the fact there's same PCI being swept, but different indexes. And the way it codes this index, I'm not going to details, but it's some interesting combination between DMRS for MIB, plus some payload in need, but there is some means that we can decode different beams, and that is how somehow you can define the cell coverage in NR. Like as long as I can detect those different beams with SPCI, I am under the coverage of a given cell. So this is basic stuff, and here just a recap on what we discussed last seminar about state transitions, right? And here I just show that in connected modes, the UE is connected to a P cell, and that's usually the run-to terminology to say when there's single connectivity, UE is connected to a P cell. I think it's for primary, if I'm not mistaken. And here is just to show that a reception of setup, which is when the UE is transitioning from idle to connected, the UE selects a cell, and then the UE does random access and performs the procedures we discussed last week to transition to connected. And then it considers that cell as its P cell. I am connected to a cell. I'm connected to a P cell. Same with resume when the UE is coming from inactive state. And then, as I showed in the first agreement, in NR we had this, let's say, split between intra-cell mobility, which would not require RC signaling. And typically we call those beam management procedure, which is when the UE is moving around, then the UE would switch, or the network would actually switch the UE from one beam to another. And I mean, from a procedure point of view, that would basically means that the UE is listening to, let's say, PDCCH, waiting for some grants in a certain direction, and then at some point the network tells the UE, oh, now listen to another direction, and that requires some, let's say, indications for the switching, but also maybe assisted by layer one measurements. It's a bit like link adaptation if you want to, but a little bit more in a spatial dimension to a certain extent. And there are also many other intra-cell procedures impacted by this sort of beam forming aspects, especially in high bands where we actually deploy multiple beams, such as radio link monitoring, as you can imagine. Like there's also some switch that has to match somehow the PDCCH directions to a certain extent, and PDCCH monitoring, as I explained. But those are not really in the scope of this seminar. I want just to make a distinction that there is this layer one base, non-layer one base, and so on. And I had a presentation about that in the past to the mobility team. I just added a link here. There is recording also if you want to have a look. And this is just a nice animation I wanted to put. But then the focus is mainly on intercell mobility, and this is actually what Run2 standardizes the most. I guess for the layer one, mainly we standardize the signaling for it, and perhaps where the parameters are provided, in which IEs, and so on. But this is really on the Run2 aspect of it, the intercell mobility, which also requires a change of beam, as you can see. We're moving from one source to a target that also requires a change of beam, and also requires some level of measurements, and we will talk a bit more exactly about that. RC and mobility. What does mobility mean? I mean, I really like this figure. I mean, this is I don't recall now the name in English of this proof, but it's in the Olympics, right? They are relaying, exactly. So they are carrying this stick, and they have to run very fast and provide the stick to another companion that has to run very fast as well. And what is the whole point of the proof? They need to do it very fast, but they cannot drop the stick. And this is basically what handover is. Like the UE is moving around, and the base stations are making sure that the UE connection is not dropped. That's basically it. And a handover failure, for example, mobility failure is actually when the connection drops, and this process does not succeed. And as you can see, I mean, there's a lot of effort from both sides, right? It's not only from one side. There's an effort from the person giving, but there also there's a lot of effort from the person picking it up. And this is basically what happens in handover. There's some effort from both sides trying to do that that sort of process. And from an RRC point of view, mobility means this signaling flow is typically shown in the stage 2 because it shows not only the UE behavior but also the signaling and the signaling between the different nodes. So typically it starts with measurements. So there is some measurement configuration from the P cell or the source node holding the connection with the UE. And basically the node configures the UE to report the quality of neighbors around in a certain frequency. And I mean, a typical case is, okay, when a neighbor becomes better than the current P cell, please report a measurement. There are periodic measurements, I think especially, I'm not sure if it was only 3G, but especially in previous systems, this was mainly periodic, and then there was this idea, why don't you do event trigger to avoid too much signaling? Send when you trigger a certain condition, when there is actually a neighbor, better. But the UI is always measuring as long as it is configured. So upon receiving some report, basically telling, look, source, there are a couple of, or a number of cells which are better than you from a certain point of view. What should you do? And then the source may take a decision. And this is an important aspect. It's the source that takes a decision to take, okay, I think I should move you somewhere else. And it's also like one principle in connected mode that it's network. Typically, we say it's network controlled because it is the network deciding where the UI moves from and to. And in this example, in the flow here, the source is okay. Send me a measurement report. Someone is much better than me. I will hand you over somewhere else. But then before I hand you over somewhere else, you will actually occupy resources somewhere else. I need to ask this, let's say, this node that owns those resources. Is it okay if I hand over this UI to you? And this is what this handover request is about. And for that, I think a question from the target will be like, okay, but who do you want to hand me over? And by who, I mean, what is the current configuration? Can I really make this a good connection? Or do I support the services that this UI is having? So then that's what the source tells the target, like handover request is like, can you handle this UI? Then I need to tell who this UI is, and this who is basically the current configuration. And if the target thinks like, yeah, I can handle that, I would like to, then I can acknowledge that. And it's actually the target that prepares the configuration to the UI. So the source decides, but the target prepares. Yes, this UI is fine. I can take that. And look, this is the configuration I want this UI to use here. So it's the target that decides that. And that is actually forwarded to the UI into this RC reconfiguration from source to UI. And that's this step 3. That reconfiguration sync, we will check that later what it is inside it, but it's basically telling some parameters to access the target cell. Again, it's prepared by target, provided by source. Upon reception, the UI applies the message, applies the configuration, and then it needs to perform random access towards the target, and then send the reconfiguration complete already with the configuration of the target. So the UI applies the message, starts running the configuration of the target, and then sends the message with the configuration of the target. This was basic, and here I would like to go through a bit these two processes, like the RC measurements part, a little bit more in details how it is in RC, and a little bit this reconfiguration part, if we have time, partially because Henning already talked a bit about, so we may skip some aspects. So when it comes to measurements, basically this is how the network decides to trigger the mobility. We already explained a bit. But the measurement configuration indicates what and how the UI should perform measurements or shall perform measurements, and also what to be reported and how to be reported. It is signaled during the transition to connected mode. So there is another way to configure this when the UI is in idle or in active state. Pradeep will talk about that. But what we're talking here is in connected mode. So when there is a transition, and this is what I show here in the right-hand side signaling flow, UI sends a resume request. There is an RC resume message that puts the UI into connected, and that can include a measurement configuration. And then the UI sends a complete, and at that point that the UI enters connected, the UI starts to perform those so-called connected measurements. And then, of course, at some point, you start to monitor those triggering conditions, and you may trigger a measurement report. And this is what we showed before that can trigger mobility. It's important to say that, is it required to configure measurements to trigger mobility? And the answer is no. Those are independent procedures in ours. Network can out of the blue say, I want to move this UI somewhere else. Bam, just give this handover command. But typically, it's good to be assisted by measurements. It can also be changed in during handover, cell changes, SCG additions, as Patrick was saying. So you can change basically any time with the reconfiguration and the resume. There are some security aspects also to be mentioned. Mesh config does not require security to be activated before it's provided to the UI. And the reason is because the understanding is that there are not many sensitive, let's say, information that is provided to the UI in the configuration. On the other hand, the measurement report, I mean, there are sensitive information such as location because you report the cells you're listening, and then you can do triangularization. It's one of the reasons you don't really report before you set up security. So it's important to set up security before. That's required to set up security before it's reports. So the mesh config is primarily a list of what we call RRM measurements. And RRM, at least when I started to work with it, was a very confused word because it means so many things. I mean, first time I heard RRM, I thought radio resource management algorithms, meaning scheduling. But that was more from my academic background. But here it's a completely different thing. Like the RRM measurements means like, yeah, you're allocating resources in different cells, and then you perform these layer 3 measurements. That's basically the best synonym to RRM measurements. But it's common wording around to talk about RRM measurements. And what I call an RRM measurement from a configuration point of view is basically a triplet. And the triplet comprises a measurement identifier, a reporting configuration, and a measurement object. And we will talk about these three later. On the right-hand side here, you see that in the mesh config IE, you basically provide a list of measurement objects, a list of reporting config, and basically a list of what we call mesh ID to add mod. To just make this simple, I guess this add mod thing is just like a list of these triplets, basically. And the reason is to optimize a bit signaling. So you just provide a list, but you can repeat some of them. Like these measurement objects, for example, is just frequencies. So you can just provide one A3 event, for example, some event configuration, but use that same configuration with pointers to different frequencies if you want to. But it's just a signaling trick. And then there are a bunch of common parameters which are applicable for all measurements. Like the S measure thing that UE starts measurements only when the P cell goes below a threshold. Then there are some measurement gap configurations, which is also something more generic for all measurements. And then filtering configurations, which are applicable also for the different frequencies. First concept that is important is this measurement object. It basically tells, first of all, what to measure.
Please, can you repeat what that S mesh config is?
S mesh config. I didn't say anything about S mesh config. I said S measure maybe. So, yeah, okay, yeah, that's the name of the IE. It's the same thing actually. Did I respond to your question, Yuan?
No, well, you said something about the U doesn't measure until something.
Yeah, when the network configures that threshold, that basically means that the UE does not start to measure anything except the P cell until the P cell goes below that threshold. It's a little bit useless parameter, except for if you are configuring measurements only for coverage-based handlers. And the reason is because, yeah, you can only start measuring the quality of the P cell goes below, but for example, if you want to configure measurements for carrier aggregation, DC, you will never use it. And that's what happens in practice. Nobody ever uses it. Next slide. Okay. Measurement object, what to measure. Basically, we measure reference signals. Again, a lot of Roman people know what these are. The quantities is basically what exactly is the measure. I mean, it's the quality of power, something related to interference, and so on. And those are the three metrics. And as in LTE, an important feature is that we don't need to tell the UE an explicit list of cells. This is a very important feature that was introduced in LTE. So you can just give the UE a frequency, and the UE can blindly search for PCIs in that frequency, thanks to the different properties of those signals and the easy way to do the matching filtering and so on. And
but I guess you can provide a certain cell or list of cells.
Yeah, you can if you want to, but you don't have to.
Thanks. Thank you.
So, and the NR design leads to some changes. I think we briefly commented that this PSS SSS transmitted in beams, which is this SS block concept, which I show here in the right-hand side. And perhaps another change, which is also significant, is the fact that you can have not only sparse, as I show here, up to 160 milliseconds, but the fact that it's also variable. So this is variable and sparse, and there are different values you can have for different frequencies. In LTE, it's basically 5 milliseconds, right? It's fixed 5 milliseconds. And another more serious thing is in LTE, you actually have something in between, which are the so-called CRSs. The beautiful CRSs that we got rid of them in NR because of many reasons, such as energy efficiency, but they will create some issues at some point. or the lack of them may create some issues. Um, then another thing that was introduced in NR was the fact that RRM measurements can be based on two different reference signals. In LTE was mainly the CRSs, the cell specific, but in NR you can tell the UV, I want you to perform measurements based on SSBs, or I want you to perform measurements based on CSIRS. So for each measurement, I can tell what I want the UV to measure. In the case of SSBs, I can do this thing I explained as in LTE, that I just tell the frequency the UV finds. In the case of CSIRS, I need to give much more information, such as bandwidth or exactly frequency, where the UV acquires sync. So from that, you can feel that doing CSIRS measurements is a bit more complicated. And even to the point that even in round 4, I don't think up to now it is provided requirements for that. So they're still working. But it's a bit more complicated, but we have signaling for it. We're still correcting things here and there, but it's there. I think one of the motivations when we introduced the fact to have these two different reference signals was that CSRSs may be beamformed with narrow beams and SSBs could be beamformed with wide beams. And the thinking there was to have the flexibility to tell the quality of a cell, not only based on one type of beamforming configuration, but perhaps a narrow beam configuration also. And one of the thinkings was that perhaps you want to beamform control channels with wider beams, but perhaps some data channels with narrow beams, something like that. That was a bit of thinking. And you wanted maybe to take a handover decision based on the fact both wide beams and narrow beams in a given neighbor cell are actually better than the P cell. So that was a bit more flexibility. Still a bit to be seen how this is going to be used in practice, if it's going to be implemented and how. But that was the thinking to introduce these two different reference signals. And another thing was that the CSIRSs, they could be transmitted more often. In the case you deploy, for example, cells with very sparse SSBs, in principle, you could, for connected UVs, only for connected UVs, have CSIRSs with higher granularity and more frequently transmitted, so that you increase accuracy for connected mode measurements. But you still have the idle coverage, rely on SSBs for the idle UVs. That was a bit the thinking. Again, the measurement object, and this is only the measurement object. The measurement object also tells the UV what to measure. And I explained a bit in the frequency domain, this ARSCN. It's very similar to LT. I tell the UV, this is the measurement object. This is the frequency you should search for cells. But the complication in NR that does not really exist in LTE for the basic LTE, it exists for the DRSs before. Some LTE experts raise their hands and say, no, you're wrong. But in the basic LTE mobility solution for the CRS based, CRSs are everywhere in the band and they are transmitted every symbol. So basically, there's no need on the time domain to tell where they are transmitted. But in NR is different, especially if you have these periodicities that could be larger than 5 milliseconds. I mean, you would need to introduce this concept that existed in LTE for other signals, which is this SMTC concept, which basically tells where the UE is required to search in the time domain for this. And that's great. I mean, we can save energy in NR because we have the possibility to have these sparse periodicities. But that does not come for free. That does not come for free. I mean, it requires some network synchronization, as you can imagine. Different nodes have to pack all signals that I want, or the network wants the UE to detect within that window. So every time I deploy a new node, I need to make sure that those signals are somehow packed into the configuration I'm providing the UVs in each base station where this is transmitted. I personally don't really know how challenging this could be implementation-wise, but I hope you people are solving that. But what I could say, it is more complicated than LTE for sure, and it complicates quite a lot the configuration of gaps, because then there has to be some coordination. The gaps is basically the time domain where the UE needs to not transmit data to measure and so on. And I had other issues that we may discover later when this gets implemented. Mm-hmm. Yeah. 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 They can be later. I think the whole point is like.
Can you repeat the question? It was impossible to hear the question on the phone.
Okay, sorry. Matthias was asking something about the figure here, whether the SSPs have to be packed into this blue part here. And I think the question becomes relevant, especially if you think of, let's say, the other nodes transmitting their SSPs. And everything has to be within the SMTC window, but the SMTC window duration could expand to multiple SSP durations. So they have to be synchronized, but they don't have to be transmitted at the exact same timing. So I can expand a bit. The whole point is it has to be within the window, but it doesn't have to be. Depends how long the window is. If you pack the window too short, and the size of a single burst, for example, then you have to really be synchronized. So it's a trade-off between network synchronization and how much time you want the UA to spend performing the measurements or to detect them. For the same cell, yes. For the same, there's a periodicity. That has to be the same. Yeah. No. Those are periodicals, well defined. Yeah, he was talking about showing the figure, the shifts between the SSBs. I didn't explain in details, but there is this concept of SSBs and SSB bursts. So basically, a burst could be, let's say, there's a burst, but simplified, this burst is basically all those beams that could be transmitted within that packed window, and they are also for each beam. This is also periodic. Yeah. So the MO also tells how to measure, not only where to measure, but what to measure, but how to measure. And in NR, there is this concept of cell quality derivation because of beamforming. Basically, this is specified, and it's been agreed to have this average of n best beams plus the ones above threshold. And n is and the threshold is configured also in the measurement object, basically. And those parameters are configured per RS type, and this is like how they are sort of standardized. So there's the threshold for SSP, threshold for CSRS, and N for SSPs and N for CSRS. And this is what we call the measurement model, and that is where we go a little bit beyond the MO. So basically, you have this layer 1 filter, and you have these beam measurements for each of the beams. Then you have this beam consolidation and selection, which is basically this threshold we discussed, but also the number of beams you picked and how you average them to define the cell quality. So at the end, you will have a cell RSRP, for example, or a cell RSRQ, but those are based on these layer 1 beam measurements. And then you do the evaluation criteria in the same way as in LT. These thresholds for the cell quality derivation, as I said, they are configured in the measurement object. The cell level layer 3 filter is this quantity config I briefly mentioned. It goes in the mesh config. And this evaluation of triggering criteria is basically what we call the events. I will talk about in the next slide. Then there could also be reporting of beam measurements, because here it's just about the cell quality and sending cell measurements, but it can also be reporting of beams for each cell. And that is also configured in the measurement object framework. In a nutshell, you could ask, like, why do we need beam measurements if we have cell measurements? And there are many different explanations. I think one of them, at least the one I find interesting, is that the one we thought about. It's about this ping pong effect, that you may want to go to a cell that not only is good, but you want to know how many beams can you detect there, how good they look like, are they stable or not. Perhaps use as a criteria also to make a decision for each cell you go to. Like, this cell is equivalent to that other cell from a cell quality point of view, but I will move it to the cell where you can detect more beams. It seems more stable, more likelihood for you to remain there. It's a bit the thinking. Report config is also an important aspect of the measurement object the measurement configuration. You associate that to a measurement object, into a measurement identifier, indicates what the UE reports, and hence what shall be measured. I don't go in details here, but what is important at the end in run 2 is what the UE reports. Then we have this so-called AX and BX events. I don't go into details of that. It's just like LTE, as it says here. But I guess I gave already the example of this A3 event for handovers, where you trigger something when the neighbor quality is better than the P cell and offset or an offset. The signaling structure is slightly modified. We have this layer 3 filter being reporting, as I discussed. Why? I explained a bit this ping pong optimization, but it's also efficient for contention-free random access. I will explain that at the end why. A typical configuration, n equals to 1, so we don't bother to do any averaging, but it's good to get reported a certain number of beeps. This is a bit the signaling structure, report config. You can choose event triggered is the one about this triggered report discussed here. We can also choose the RS type for the cell quality derivation. We already talked about CSRS and SSB, and you can also choose being reporting. There are some parameters controlling. You can choose to report just the indexes, and I briefly mentioned how to detect the indexes of the SSBs and so on. Or you can include measurements also. This is our friend SSB, if you are curious. Why 2 RS types? I already mentioned different periodicities, possibility to have different periodicities or different bin configurations. Sorry for insulting our layer 1 colleagues again with those flowers, but in run 2, at least this was very common, at least some time ago, to abstract and illustrate a bit how the bin former look like, but we know in reality they don't look as beautiful as those drawings. But that was a bit the thinking on this, the different reference signals. Oh.
But so those two kind of beams, they exist at the same time, or?
Yeah, they can. They can exist at the same time, and the network can configure the UV with two different measurements basically, and the UV can measure them at the same time.
But aren't they sort of like when they overlap? How will the UE? Like for example, the UE where it is now.
Yeah.
It will be measuring that the middle narrow and the middle wide beam, sort of.
The UE is told actually. I mean, the UE is told the frequency, right? To measure.
Sorry?
For the SSP case, the UE is configured with the frequency to find the PCIs, and then you will find the beams within that PCI for a given cell. For the CSRS, you need to tell a specific associated cell, and then you need to tell exactly where the CSRSs are being transmitted. This is one fundamental difference, that you need to give much more information to the UE so that you can find the CSRSs. I need to wrap up, unfortunately. I'll just go briefly here. So this is a bit the structure of the measurement report. It's just organized per cell, and then you have the cell ID and some measurement ID. I guess here is basically what we have shown for the case of the A3 event. For the reconfiguration with sync, I guess the delta from LTE is very simple. Here I go very quick because Henning talked a lot about this last time. But the message name changes a little bit, and that's you will not find the name handover command in RC if you search for. Don't get frustrated. There is still handovers going on, but it's more like a terminology thing. And for those familiar with LTE, instead of mobility control info, you will have this reconfiguration sync field name, and that's what tells the UE that this is a handover. It's not any kind of reconfiguration. The signaling structure changes a bit. It reflects this CU-DU split. We have this radio barrier config, which mainly some sort of CU configuration, and the cell group config, which is basically DU. This is where the layer 1 and MAC parameters are actually configured. Optional key refresh, that is mandatory in LTE. Like if you have a centralized architecture, central CU that has same PDCP, you could do handovers without change. I don't see much benefit, but it's possible. Other impact from layer 1, I'm not going through this, but you can imagine this whole bandwidth partitioning changes lots of things. There. Here is, I'm just repeating Henny's slide. It's just to make a connection so you can see. And the important message here is that it is the target that decides the UE configuration in targeting handover. It's an important principle already described. And then, of course, It is the target CU and the target PU that defines what parts are relevant in which context. It's just to make a link between the two presentations. And this is the reconfiguration with sync. Looks very similar to the mobility control info. Here you can see this so-called SPCell config common. And this is basically mostly what we have in system information. And the reason is that we don't want the UE to go to the cell and then, we don't want to give handover command to the UE and then let the UE find parameters to access the cell in sysinfo. It takes too much time. So then the target already gives that to the UE, which has the random access configuration. At least the common one, and then of course there could also be the dedicated branch configuration also. UE identity, this is basically a CRNTI that is given to the UE to say this is what we should use in target. And then this SMTC, remember I talked about this synchronization thing. The UE needs to find the cell, the target cell, right? And then I need to tell in the time domain where the target cell really is. And that's how I tell SMTC. So the UE finds and then performs random access. And this failure timer that runs, that's how much time the UE has to access the target. If that expires without the UE access to the target, then you consider handover failure and that's reestablishment and so on. The last, this is my last slide. Before the last slide, this is about the bean selection random access at the target cell. Only reason I touched upon that is because there is some bean forming happening here, also bean related changes. But I expect Mats or Jose, I think it's Mats who will talk more about MAC procedures. He will definitely talk about that a bit more. But in the context of handover, at least in a nutshell, the reconfiguration with sync requires random access with target. So I need to do random access with target to finish the handover to target. This is similar as LTE. You support both contention-based and contention-free. And perhaps one of the differences, at least, is that there is a built-in bean selection mechanism. And how does that work? Like, first, the downlink beam in the target is determined by random access. So the UE, when I know the target, right? I know the PCI of the target I need to go to. So I need to select a beam in that target. So I will do measurements. I will select something. And I need to select something above a threshold. And then there is a built-in mapping in this configuration between the beam I select and the RAT resources that I can use. And that is also, of course, variable. But basically, when I select a beam and select the RAT resources and send a preamble, network can detect, okay, I received the preamble in this resource. I received that preamble. So I know in which downlink beam I need to send a random access response. So this is why it's a bit like a random access built in, beam selection process built into random access, that by doing random access, the target knows which downlink beam the UE is starting. And remember what I told about reporting beams. And contention free, I would come back. So this is what this is about, that when the UE report the beams from a target, the target has the possibility to allocate contention-free resources on a beam level. And the advantage is that I don't need to give resources for all possible beams in the target. I can do a subset. So, this UE is coming to me, and this UE is listening to my beams 1 to 5. So I want to give contention-free resources, but I only need to do for 1 to 5 because it's likely that when it comes, it will come in 1 to 5. So this is a bit one of the reasons that the target, that the UE report beam measurements. And as you can imagine, since the target is the one deciding these contention-free resources mapped to beams, there is a transfer also in the handover request from source to target about that. Target sends random access response in the downlink beam that the UE selects. The communication continues with these beams. But then, of course, after this first beam selection, then the target continues as usual, like with layer 1 beam management, which could be a refinement or a switching, and that becomes in layer 1 mobility again. To wrap up, this is my last slide. This is the procedure again, and here I just want to show you that first, these procedures are sort of independent, but all of them sort of relates to these mobility procedures. We have these ROC measurements, and it's basically 5.5, a session called measurements in 38331. This, you can find everything that you need to measure. needs to report, how it is configured, what are the conditions to trigger those events, the content of these reports, and so on. Then you have this RRC internode messages, and here is a bit confusing because there are some parts standardized in RRC in chapter 11.2, but there are some parts into the run tree specs. Typically, best way I explained is that in RRC, you will find many things which are more radio related. It's not really networking related, but a lot of things which relates to the UE configuration or UE aspects and so on. And then you have the RRC reconfiguration. It's not only about mobility, it's about any reconfiguration you give to the UE, as Henning explained last time. The one specific for mobility relates to the reconfiguration with SIG, this 53552. And that is the configuration that we talked about. Then you give the UE a new PCI, you give the UE this new CRNTI, RAT resources, timer, SMTC, target, and so on. And then random access, which again is used in many other different procedures, but also in mobility. And this is why am I showing this slide? Is because when you say like, please present something about mobility, and then when you work with protocols, you need to sort of pick things a little bit. Okay, I will talk about random access, but random access is also used in many different places. Same with measurements, and same with reconfiguration and so on. So a good place to look into a more overview, including all these aspects, but to start with at least would be the stage 2 spec, which is 38300. That's it. Thank you.
Okay, shall I start, or is there any question to Ikarov before? Seems like none, so I will start. Yeah. Okay. Yeah. Just to continue from where this seminar is heading. I mean, now Ikarov pointed out quite a lot about connected mode mobility, and now we will move on to the idle and inactive mode mobility, wherein there is not much information available at the network, so it is what we call a UE based mobility. So if you go to the next slide, yes. Okay, yeah, this is not yet updated. There is a small typo here, but again, what